Welcome back to UppSense, the Uppsala University Census team. In this 4-minute pitch, we'll be going through all the major facets of our biosensor. We'll be explaining the sample transport, molecular recognition, physical transduction, and data processing, as well as showcasing the feasibility of our biosensing device with our scientific results. To start off the analysis, the plasma sample is injected into a microfluidic chip, which by laminar flow diffusion separates the VPA from the plasma phase into a secondary buffer phase, which effectively cleans the sample from larger molecules. Using COMSOL multiphysics modeling software, we have been able to optimize the flow rate such that we maximize VPA diffusion while minimizing the diffusion of blood protein and reagents. Thereafter, a mixing step occurs to let VPA interact with our reagent. Here, reagent refers to coated gold nanoparticles. The coating consists of a molecularly imprinted polymer, or MIP for short, which is responsible for the molecular recognition. We have synthesized a custom polymer around 50 nanometers colloidal gold particles to selectively bind VPA. Our very own quantum chemical DFT calculations at PBE, Purdue, Berkeley, and Sohoff level of theory have shown binding between VPA and the functional monomer of the polymer. The MIP ensures that VPA is selectively brought close to the gold nanoparticle, an integral part of the physical transduction, which happens by surface-enhanced Raman spectroscopy. Raman spectroscopy is a well-established spectroscopic method which measures vibrational properties of molecules. Historically, it has been limited by a lack of sensitivity, but advances in instrumentation and methodology have increased its applicability. One such methodology, SIRS, surface-enhanced Raman spectroscopy, is a distance-dependent phenomenon which increases Raman spectroscopy signal intensity at colloidal metal surfaces. Utilizing a green laser and an optical detector, we can perform Raman spectroscopic measurements which selectively boost the VPA signal without increasing background signals. The data is processed via peak picking and integrating the peak area against the calibration curve. The spectrum as well as integrated result are shared in cloud server and can also be observed on our user-friendly touchscreen display, as can be seen here. Our biosensor has the potential to measure VPA over the entire therapeutic range. Literature states that SIRS is capable of detecting up to single molecule concentrations. The main challenge faced by our team was the development of a coating protocol for our novel imprinted polymer, which we succeeded at, as evident by our experimental results, which show the release of VPA and a corresponding signal decrease from our coated particles. Furthermore, our sensing setup, which is depicted here, has the possibility to expand its biosensing capabilities simply by altering the molecular recognition polymer. A different composition can have the ability to observe various analytes separately or simultaneously, as long as they are separated on the Raman spectrum. It should be mentioned that although our biosensing system has been developed for plasma analysis, it could be used directly on blood samples as well, since our initial separation step already separates VPA from larger molecules, proteins, and cells. We want to take this opportunity to thank our generous sponsors for their support along our year-long journey, and you, the audience, for your attention. Thank you very much.